the aim is to introduce the importance of mixing to industrial processes. The key thing is highlighting the benefit of considering this early in process development and not spending one's time solving mixing problems once they've appeared, but trying to preempt problems by thinking about it early on. I'm going to give some examples from consultancy work we've done to show where mixing performance has been a significant issue and mixer design has been important. And unlike other presentations, the aim of this is very much not to include any equations. So we're giving examples and talking about the key issues rather than trying to do any calculations or sums here. We'll come on to that later on because we can give presentations covering those topics in quite a bit more detail. So one of the things that certainly at BHR we find very interesting and very useful about mixing is, as a topic, it's a real issue across many industries. We can see a list of some of our consultancy and consortia clients cover everything from pharmaceutical to mining industries, food and drink, to personal care products and water treatment. Very different environments, very different products. But even though the products and the mixer geometries can vary significantly, key processes, key problems and issues, and the controlling mechanisms limiting the mixing performance very often remain the same, independent of the application. And that's good for us because it means we can work for lots of different industries. So why do we mix? And the obvious first answer is we mix to reduce inhomogeneity, to make everything more uniform. And that could be looking at simple liquid phases or trying to distribute solids or gas within a liquid phase and make everything more uniform. However, in some cases, people need to make things more uniform to make a product that can be sold. But very often, we're doing mixing to achieve some other process result. We might be modifying the pH or doing some transformation involving a change in the rheology or the properties of the material we're mixing. We may be adding materials simply to adjust the concentration of some component. You may be interested in creating a dispersion of two immiscible liquid phases. And so we need to put energy into the fluid to produce that dispersion. Very often, we're mixing to help a chemical reaction. And that's a big part of the work we do, is looking into how does that occur. And sometimes we're mixing just to enhance heat or mass transfer. Very common processes. So one of the key things, we're talking about chemical reactions. What mixing does is it affects the reaction environment. It affects the zone where chemistry and other things are going on. So mixing affects the distribution of flow and turbulence inside a tank. And in a big stirred tank like the fermenter you see in the picture, there are very significant variations in the level of fluid turbulence and the velocities throughout the geometry. Things are very well mixed and intense close to the impellers and much less intense near the surface or close to the walls. And that has a significant impact on the concentration of reagents. If you're mixing two materials and there's a reaction occurring, depending upon the location, the concentration of the different reagents may be different, and that may lead to different products. In a fermenter, particularly in very large vessels, the local values of pH and dissolved oxygen can vary very significantly different locations in the vessel, and that can have a knock-on effect on the product. mixing can affect the distribution of phases, so how well dispersed gases and solids are. And it can affect temperatures and even pressures, and local operating conditions can be affected. And all of these different factors ultimately can affect reaction rates, because the local reaction rate is a function of all of these other variables. So the key thing to any process is never start assuming the process is well mixed. The standard assumption in any textbooks is, assuming a well mixed tank, do the following. The correct advice is never assume some mixing vessel is well mixed until you've confirmed that's the case, because things are never perfectly mixed. What you want to do is ensure that they're sufficiently well mixed to produce your product. So we've talked about why it's important. Where is mixing important? Well, because of the things we've seen already, it's important at pretty much all stages of the process. Everything from the synthesis of intermediates or active ingredients early on in the development of a drug product, let's say, but mixing is also very important when it comes to the final product formulation. So at all stages through a process, from preparing ingredients to their processing, at a range of different stages, mixing can affect a whole range of topics. It has a big impact on process timescales, and that's very frequently something that we come across in projects, is looking at how can production rates be increased, how can batch scheduling be improved by optimizing mixing. And it also has a big effect on, not surprisingly, on downstream separation. And that's where we've got to be very careful to make sure that some process problems, maybe a downstream separation problem, isn't always considered as a mixing problem, but very frequently the cause of the problem is upstream, and if the mixing's improved, then there's less issue with separation afterwards. So it should always be considered, even for further downstream processes. So if you're looking at developing a process, where is mixing important? Where has it got to be considered? And the obvious starting point is as early as possible in the chemistry development or the process development. We've got a picture of a stirred beaker, but obviously process development can go on in much smaller scales, in microvials and so on. And even there's work being done looking at how mixing can affect product quality or reaction or production with taking selectivity of different components. When we've got early stage process development, key thing to do, if at all possible, is check and look to see if there's any sensitivity to mixing, and to do that at an earlier stage as possible. Because even if you find at the lab scale that mixing does affect the production, then you know to take more care and consider it later on. Sometimes it's just a case of doing your lab experiments at a range of different mixer speeds and see if that does have any effect on the product. And it's rather sadly, it's all too frequently that simple test has not been done. And then, once you've got some, often you want to start scaling it up to some pilot scale rig, then we need to consider how to translate the mixing performance to give us the same product and distribution of products at the pilot scale, where we may be dealing with a few liters or tens of liters or maybe even hundreds of liters. And when we're working at that scale, a lot of what we're looking at how to do is to optimize performance of the reactor and understand the optimum operating conditions and the sensitivity to different variables. And mixing can play quite a significant part in doing this.